Not all reactions occur in one step. Usually, they occur in multi-step. Reaction mechanism shows step-by-step series of two or more simple reactions that combine to form an overall reaction. So what reaction mechanism does, it describes in detail exactly what takes place at each stage of an overall chemical reaction. So to help you out, you need to understand some of the vocabulary for this chapter. The overall reaction is the sum of the elementary steps. It's pretty much doing Hess's law. You add all the reactants together, you add all the products together and cancel out the things that are the same on both sides. The overall reaction may also be known as the complex reaction. That's another word for it. Elementary steps here are a series of simpler reactions that combine to form complex reaction. Intermediates are substances that are produced in one elementary step and consumed in another. So what happens is if you have multiple elementary steps, it will never appear as a reactant in this first step, and it will never appear as a product on your last elementary step. It will only appear somewhere in the middle, and it will cancel out. A catalyst increases the rate, but is not consumed by the reaction, and it remains unchanged. So when you write the overall reaction, it will not appear in the reaction itself. However, in the elementary step, it will appear in step 1 in the reactant side, and it will appear as a product on the last elementary step. But when you apply Hess's law and cancel everything out, the catalyst will disappear. The rate determining step is always the slowest step, and this will limit how fast the reaction occurs. So if the reaction has 10 elementary steps and the first step is the slow step, that is the rate determining step, and we don't care about steps 2 through 10. We only work with step 1. If we have 7 elementary steps and the rate determining step or the slow step is step 4, we must go through step 1, step 2, step 3, and step 4, and everything that follows step 4 we ignore. Molecularity of a reaction is the number of molecules reacting in the elementary step of the reaction mechanism. These molecules can be the same or they could be different. There are 3 types. The first type is uni. Uni means one, so there is one molecule or molecular. So unimolecular general equation looks like A, which is one molecule, yields a product. So if I write the rate equation, the rate is equal to K brackets A. Because when we use elementary steps, we use the coefficient of the balance equation as our exponents. When it's bimolecular, there are 2 molecules, and so they could be 2 A's, an A plus an A yields a product, and when that happens, the rate equation becomes K, A in brackets, to the second, because the coefficient in front of A is 2. We could also have A plus B, that is still 2 molecules, that yields a product. When I write the rate equation, rate is equal to K, A in brackets, B in brackets, and that represents 2 molecules. Coefficient of A and B are both 1, so the exponent is 1. For tertiary, there are 3 ways you could write it. It could be 3 A's, or A plus A plus A, which is just 3A, yields a product. So my rate equation equals to K, A in brackets, to the 3rd power, because the coefficient again becomes the exponent. Or you could have 2 A's plus a B, and that's also 3 molecules, yields a product. The rate is equal to K, a squared because there are two a's, so the coefficient in front of a is 2, so that becomes the exponent, and b, which has the exponent of 1. Or we could have a plus b plus c produces a product, and so the rate equation becomes k, a in brackets, b in brackets, c in brackets, all to the power of 1, because the coefficient is 1. Molecules A can be replaced by B or C or any other letter. The total number for uni has to be 1 molecule. Total number of molecules for bi has to be 2. For tertiary, it has to be 3. When you are solving problems with reaction mechanism, you are always going to use the coefficient of the balance equation to write your rate equation for the elementary steps. These coefficients will become the exponents. These are some steps that will help you when writing reaction rate for mechanism. You will use coefficients. You will use the coefficient of the balance equation to write the rate equation for elementary steps. These coefficients will become exponents. If you have multiple elementary steps, whenever it is fast in equilibrium, you have to have a double-headed arrow or an arrow like this. These double-headed arrows represents equilibrium. In addition, you must label the K constant. So in the forward reaction, if it's step 1, it will be K1 for step 1. In the reverse direction, it will be K1, but it will be a negative 1 to denote that it is going the opposite direction. So for this second arrow, it's the same thing. K1, K minus 1. Since they are at equilibrium, and equilibrium means the rate or the exchange rate is the same, the rate in the forward reaction must equal to the rate in the product reaction. Anything that is the slow step, this is your rate determining step. Any elementary steps that follow the slow step, you will ignore. And when we write the rate equation, we only write it for the forward reaction. Please note here, for overall reaction, that means I add all the elementary steps and get a final reaction by canceling out all the intermediates and the catalyst. We do not use the coefficients of the balance equation for the rate equation. We need to solve this experimentally or it will be given to you. Pause the video and try this example on your own and then check your answer. So this equation has 3 elementary steps. The first one is the slow step, and the next 2 that follow are fast. When we do reaction mechanism, we always look for the slow step because anything after the slow step we ignore. For A, what is the rate determining step? It's going to be step 1 right here because it's the slow step. The reaction cannot go any faster than what is happening in the slow step. Does the reaction have a catalyst? To determine if the reaction has a catalyst, write the overall reaction. Similar to Hess's law. So we're going to add all the products together, all the reactants together, and cancel out anything that are the same on opposite sides. So I could cancel out N2O2. They appear on opposite sides. I could cancel out N2O and N2O because they appear on opposite sides. Now I'm going to add everything on my reactant side. So that's going to be 2NO. There are 2 H2s right here. So H2 plus E2 is 2. This is going to yield 2 waters plus 1 N2. So this is my overall reaction. So in this equation, there is no catalyst because if I look at my first elementary step, in my reactants, we have NO and that is our only reactant. And if I look at my last step, we have H2O plus N2. So there's nothing that is the same as a reactant in the first step and as a product in the last step that cancels out. So this problem has none. And what is the overall reaction? It is what we wrote here. 2NO plus 2H2 yields 2 waters plus N2. What is the rate law? Since the slow step is the first one, we know this is going to have a K of 1. So my rate is equal to K brackets NO. Since this is an elementary step, this 2 is now the exponent, and my K was a 1, so this is K1. And we can simplify this to K NO brackets 2. So this is my rate law. In this example, for the reaction 2x plus y yields z, the rate law is K brackets y. So they already gave you the rate law. They want you to identify the intermediates, any catalysts. They want you to write the molecularity of each step, determine it, and which reaction mechanism is consistent with the rate law above. To identify the intermediates and catalysts, the first thing you want to do is determine the overall reaction by adding the two steps together and canceling out anything that is the same. So the m's cancel out because they appear on opposite side. So the equation becomes 2x plus y yields z. So we know the intermediate is going to be m because it appears in the first step after the reactants, and it disappears before it becomes a product at the last step. So here M is your intermediate. There is no catalyst. A catalyst must appear as a reactant in the first step and appear as a product on the last step unaltered, and when I write the overall reaction, it disappears, it cancels out, so there is none. So the molecularity for the first step is going to be bi, because we have one molecule here and this is my second. For the second equation, it is also bi. We have 1, 2. The rate law is the following. It is determined by the slow step. So the first thing I'm going to do is label my constant. I'm going to label this K1. So my rate is going to be K1 brackets x brackets y. And so this is the rate law for mechanism 1. So this is mechanism 2. So first we're going to do is write the overall equation to determine if there are intermediates or catalysts. So again, the m's cancel out here, and I add all the reactants and the products. So this becomes x plus y yields z. So the m is an intermediate here because it appears after the reactants in the first step. It is used up and disappear before it becomes a product on the last step. There is no catalyst because a catalyst must appear in the first step as a reactant and last step as a product and cancel out in the overall reaction. So the molecularity for the first equation is uni because there's only one molecule here. For the second step, it's going to be bi because we have 2. X and M. The rate law again is determined by the slow step. The slow step is the first step. So rate is equal to, we label this K1 brackets Y. This is mechanism 3. First thing I'm going to do is determine if there are intermediates or catalysts. So I'm going to cancel out, there's an M on opposite sides. There's an N on opposite side. Now I'm going to add, nothing else cancels out. So it's going to be Y plus 2X yields Z. M and N are your intermediates because they're consumed or disappear before the reaction ends. There is no catalyst because it needs to appear as a reactant in step 1 and appear as a product in step 3. So this is our overall reaction. My rate law is going to be determined by the slow step. So this is my rate determining step. If we label this K1, the rate is going to be K1 bracket Y. The first step is uni. There's only one molecule in the reactant. The second one is bi because there's 2 molecules in the reactants. And step 3 is also bi because there's 2 molecules in the reactant. So now we have to see which mechanism proves this equation. So the rate law looks like this, K brackets Y. So it can't be this one. So this is not possible. Mechanism 2 is possible and mechanism 3 are both possible. The answer is mechanism 2 and 3. And so you could rewrite this as rate K brackets Y. And this too could be K brackets Y. Pause the video, try this problem on your own, and then check your answer. So determine the rate law for the following reaction mechanism. There are 3 elementary steps. The first one is rapid and in equilibrium. So when it's written as rapid and equilibrium, sometimes you will only see a single arrow. That means you must put a double-headed arrow in. So at equilibrium, the rates are equal and opposite. Step 1, we usually by convention write K1 in the forward direction. In the reverse direction, we write K minus 1 to denote it's in the opposite direction. The second step is slow. So we're going to label step 2 as K2, and it could only go in the forward direction because it's the slow step. Anything that follows the slow step, we are going to ignore when we are doing reaction mechanism. Start by writing a rate equation. Rate, remember, in general is equal to K times the concentration of something. So for the step 1, the forward reaction, I know my K1 is my K constant, and we have A in brackets, B in brackets. The coefficient of A and B are 1, so the exponent is 1. Since this is in equilibrium, the rate in the reverse direction is also equal, but the K constant is K negative 1, denote it's going in the opposite direction, times. So in the second equation, which is my slow equation, we only look at the reactant because it's the rate determining step. So the rate is equal to K2 because it's the second step, Q times A. So what we want to do is solve for the intermediate. If I look at this equation, the intermediate is going to be Q. So I'm going to solve for Q. So using the first equation, I'm going to solve for Q by dividing both sides by K minus 1. And when I do that, Q equals K1 over K minus 1 brackets A brackets B. Now what I'm going to do is substitute this into the rate equation from step 2. So that's going to be rate equals to K2. And what is Q equal to? Q is equal to K1 over K minus 1 times A times B. What I did was for this Q, I solved for Q using the first step equation, and I substituted in for Q. So what we have here is a 2 equation, 2 unknown, and this has to be multiplied by A. Now I'm going to clean this up. We could say that since K1, K2, and K minus 1 are constants, I could say K is equal to K1, K2 over K minus 1. So when I rewrite the rate equation, this whole thing right here is going to equal to K. We have a A in brackets and another A in brackets, so that A squared times B in brackets. So this is the rate equation for this equation. If I want to determine the molecularity, I look at my reactants for each step. They are 2 molecules, so this is going to be bi. In the second one, there's 2 molecules, so this is also bi. Third one has 2 molecules, so it's also bi. Intermediate here, there are 2 of them. It's going to be Q because they cancel out and they appear in the middle, and then R. There are no catalysts here. In general, writing reaction mechanism will involve multiple elementary steps. Look for the slow step. Any steps that follow the slow steps you may ignore. If it's rapid or fast and in equilibrium, you must have a double-headed arrow. Going in the forward direction is going to be a positive subscript. Going in the opposite direction, you have to put a negative saying it's reversed. Anything that is fast and in equilibrium, the rate of the products will equal to the rate of the reactants, or you could say the forward rate is going to equal to the reverse rate. And the variable that you are going to solve for is the intermediate, and plug it into the slow step. Once you plug it in, simplify your equation. Remember, elementary steps use coefficient of the balance equation as exponent. Overall reaction, you cannot use the coefficient. You must determine the rate law experimentally, or it must be given to you.